Welcome to Integrated Metal Roof Retrofit with multiple energy-saving technologies. This course qualifies for one AIA CES HSW learning unit. To receive credit upon completion of the course, you must take a 10-question quiz. Scores of 80% or higher will receive credit. However, you may take the course as often as necessary to pass. Upon conclusion of the course, should you have any questions related to the metal roof retrofit system described in this course, a list of contact names and email addresses are provided for your convenience. The learning objectives for this course are as follows. Examine the economic, environmental, political, and philosophical drivers behind the development of an innovative roof retrofit system, engineered to both conserve and generate unprecedented levels of energy. Understand the multiple energy savings and generating technologies employed in this new retrofit roof system. Demonstrate a complete installation of the new retrofit roof system through the use of a large-scale mock-up installation. And identify the numerous and readily tangible sustainable features and benefits of the new retrofit roof system. In 2010, the Department of Defense, through their Environmental Security Technology Certification Program, ESTCP, awarded a grant to demonstrate a novel integrated energy-efficient metal roof retrofit system using commercially available products or systems. A team comprised of metal roofing manufacturers, suppliers, industry professionals, an experienced certified contractor, MCA, the Metal Construction Association, system integrators, and the Department of Energy's Oak Ridge National Laboratory designed the integration of several technologies into a compatible roof retrofit system. After conducting a structural engineering assessment of the integrity of the existing roof structure and its load-carrying capability, the retrofit system was then installed on the 11,900 square foot roof of the Security Forces Building at the Goodfellow Air Force Base in San Angelo, Texas. The total weight of the retrofit system is 4.5 pounds per square foot. Installation was completed in June 2012, at which time the collection of data on the building's performance began. The retrofit system used at the Goodfellow Air Force Base includes integrated photovoltaics, an integrated solar thermal water air heating system, cool roofing, enhanced insulation, a radiant barrier, natural convective cooling, and a rainwater harvesting system. The Goodfellow installation project is expected to yield over 750,000 kBTU of energy per year from the energy that's saved through energy efficiency improvements to the building or harvested from solar energy generated on the roof. This video webinar will show how the existing metal roof on that building was retrofitted, and in the process, will show how the new integrated roof system increases the energy efficiency of the building by increasing the R value of the roof, improving the building's air barrier, and offsetting conventional sources of energy through the use of photovoltaics and solar thermal technologies. The Energy Star program estimates that there are over 4.8 million existing commercial buildings in the United States, with 40% of them being built prior to 1970. This was at a time when energy efficiency was not the priority that it is today. As a result, we have a large inventory of buildings that are poorly insulated and are using inefficient systems and building materials. Efforts are now underway to retrofit existing buildings to make them more energy efficient. The DoD is the world's largest consumer of energy and operates over 2.4 billion square feet of building space. Several mandates and executive orders have required the DoD to produce or procure more of their energy from renewable energy sources. Their ESTCP program is used to demonstrate technologies and building systems that can help them meet the mandates and other requirements. Today, the architectural community is significantly challenged to design all types of buildings that are more energy and water efficient, using renewable or alternative energy sources, and incorporating more retrofit concepts. The good news is that the work has already begun on the use of new building technologies and systems to implement energy-efficient solutions. A set of plans and a master specification for the installation are available upon request. Using a full-size mock-up in a laboratory, we will display the sequence used to install the materials and systems on the GAFB building. Here we see a reduced scale of a typical steep-slope pre-painted standing seam metal roof. This represents an existing roof on a building. The mock-up roof assembly depicted in this video is shown for illustrative and training purposes only. Each system design will vary based on the actual conditions found on any given project. All systems must be designed in accordance with current best practices and be built by certified and experienced installers in accordance with the design and the component manufacturer's requirements. Imagine a 25-year-old standing seam metal roof with no cool roof finish and a roof assembly with R19 insulation. That building needs to be brought into the 21st century. Our first new component to add is a sub-purlin system. The sub-purlins have undergone AIA CES 802 base test method analysis, showing that they typically strengthen the existing purlins beyond the loads added by the retrofit system. Additionally, they have been subjected to rigorous ASTM E1592 uplift testing to confirm their ability to resist wind pressures on the new roof panels. The design of sub-purlins must take into account a number of factors, beginning with verifying the type and shape of the existing roof panels and the existing purlin spacing. Once established, the engineering component comes into play by determining the design uplift capacity needed by roof zone and then comparing this to the capacity of the new panel system that will be fastened to the sub-purlins. The final fully engineered design focuses on how the new roof, when attached to the sub-purlins, will be strengthened and perform better at corners and edges, where most roofing failures occur. When necessary, the spacing between sub-purlins can be reduced by adding structural elements, which will in turn increase the capacity of the new roof. These wind uplift and other structural requirements will meet or exceed local codes, plus any additional project requirements. The 2.5-inch high sub-purlin system shown in this mock-up is identical to that used in the ESTCP demonstration project at Goodfellow Air Force Base. The sub-purlins are made of 16-gauge G90 galvanized 50 KSI high-strength steel, pre-punched to fit the existing 16-inch on-center roof panels. The first step is to attach a butyl tape to the bottom of the sub-purlin to create a watertight seal with the top side of the existing roof. This will prevent any leaks prior to the new roof being installed. The sub-purlins are designed to nest over the standing seam metal roof profiles. Then the sub-purlins are attached into the structural purlin or joists beneath the deck of the existing roof. The sub-purlins for this building are attached with 3 1/4-inch diameter self-drilling fasteners every 16 inches using a standard magnetic driver and torque-limiting screw gun. Fasteners are normally installed from left to right along the length of the part. Sub-purlins are designed to withstand additional dead loads for solar technologies that are part of the retrofit roof system. Once attached, a new platform is formed on which additional components of this retrofit roof system will be secured. The installation by a qualified and experienced certified contractor of a sub-purlin system has to be as intuitive and simple as possible, using standard tools and fasteners, which was the case on the Goodfellow Air Force Base project. Metal is a conductor of heat. As a result, installing continuous insulation with a high R value is a critical component, helping to minimize the effect of thermal shorts. Recent research at Oak Ridge National Laboratory was focused on the thermal performance of new and innovative insulated metal roof assemblies. Using the ASTM 1363, or hotbox test, this work provided an indication of the relative efficiency of the insulation and provides guidance to designers on what assemblies more closely match the calculated value of the insulation used in the design. A key result of this research showed that it is important to recognize how insulation systems are constructed, rather than looking only at the total R values of the insulation layers. On our mock-up, with the sub-purlins properly installed perpendicular to the standing seams of the metal roof, a grid work of the sub-purlins to support the standing roof is formed on the roof. Using that grid work, we then installed polyisocyanurate rigid foam insulation board. Once that material is installed, an additional 1/2 inch thick polyiso rigid foam insulation board is installed to bring the total to 2.5 inches, which complies with the ASHRAE 90.1 2010 standard for the climate zone, which is ASHRAE CZ3 of San Angelo, Texas. In this mock-up, the workers are walking on the product. However, on a real job site, walking on the rigid board is not recommended. Then reflective foil-faced sheets of 1-inch thick polyiso rigid foam insulation are installed and secured with insulation fasteners. The seams of all insulation boards are staggered to eliminate thermal shorts, and the seams on the 1-inch outer layer of insulation boards are taped to eliminate air leakage and minimize heat gain. The hot box tests confirmed that using a layer of continuous insulation, CI, added more to the overall effective R value than just using fiberglass batts. When used in conjunction with the appropriate joint closure system, polyisocyanurate insulation effectively blocks airflow, meeting ASTM 2357-05 standard test method for determining air leakage of air barrier assemblies and ASHRAE 90.1 2010 requirements. And the low PERM rating helps to reduce moisture condensation within and below the insulation. Also, the insulation, especially if it's taped, can provide a second layer of defense against any leaks in small gaps or holes from wind-driven rain. Note that the second layer of insulation covers the top of the structural sub-purlin, creating a full thermal break between the building exterior and interior. Contractors and installers can appreciate the ease of construction, as they did on the Goodfellow Air Force Base project, when rigid insulation is specified as part of a retrofit because lightweight insulation boards can be sawn or cut with a knife and then quickly installed on the structure. On the Goodfellow Air Force Base installation, this level of insulation from the retrofit, combined with some of the other components that are installed, and the existing draped batten glass fiber insulation on the existing roof system, brought the total insulation level up to R51 for the system. The U.S. Green Building Council and the U.S. Environmental Protection Agency estimate buildings account for 40% of our nation's primary energy usage, and almost 75% of all electricity consumption. According to the U.S. Department of Energy's Oak Ridge National Laboratory, in an average low-rise building, heating and cooling energy accounts for about 30% of total energy used. About half of heating and cooling energy is attributed to heat loss in cooler weather or heat gain in warmer weather at the roof. U.S. codes and standards are recognizing this and have become significantly more stringent in their insulation requirements. The U.S. military also has recognized the importance of increasing its buildings' energy efficiency. Reduction of greenhouse gas emissions related to cooling and heating loads is now a priority for all federal agencies, thanks in part to Executive Order 13514, Federal Leadership in Environmental, Energy, and Economic Performance, which was signed October 5, 2009. The R value of insulation is the resistance to heat flow. The thermal resistance depends on the type of material, thickness of the insulation, and density of the insulating material. Depending on the type of materials used and manufacturing method, R values can range from around R3 per inch to close to R7 per inch of board thickness. In the case of the Goodfellow Air Force Base demonstration project, the rigid insulation board has radiant barrier quality facers on both sides, acting as a radiant barrier to further improve energy efficiency. The glass fiber reinforced polyisocyanurate foam core, R6.5 at 1 inch, is laminated between smooth facers and was seamlessly integrated into the final assembly. The projected energy savings at the Goodfellow Air Force Base from the insulation alone is estimated to be $2,500 per 10,000 square foot of building, or more than 20% of current utility expenditures. In addition, the reinforcing material used in rigid board insulation, along with the patented chemical formula, enhances the fire resistance and dimensional stability of the insulation. These were important product attributes for the DoD demonstration project because of the high temperatures possible from the performance of the solar energy collection systems. With the added insulation secured and in place, the client wanted an optional secondary backup layer of water intrusion protection. So, a self-adhered membrane was installed on the surface, with excess material extending over the drip edge flashing. The self-adhered membrane is attached to the entire roof surface and sealed below the ridge, rake, and eave trim to complete the air barrier. After the underlayment is secured, a radiant barrier is attached to the roof. The radiant barrier is another energy-saving component of the integrated system. Radiant barriers have been shown by DOE to reduce heat gain and loss in a roof system by 9%. In the Goodfellow Air Force Base installation, the radiant barrier serves an additional role in containing energy in the form of heat in the plane of the barrier, on which an integrated and concealed solar water heating system will be installed. The synergy between the efficiency of the solar thermal systems and the radiant barrier is a benefit in the design of the retrofit system. For any type of building, water heating and space heating represents a significant percentage of the building's energy consumption. Thoughtful selection and implementation of a renewable energy system before and during construction can often yield high savings and beautiful aesthetics provided through an experienced and competent certified contractor, as demonstrated on the Goodfellow Air Force Base. The combined building envelope plus energy technology systems fall into a category defined by the U.S. Department of Energy as Building Integrated Solar Technologies, or BIST systems. These systems collect the sun's energy as heat and transfer that energy to the building's space and water heating systems via heat exchangers using environmentally friendly heat transfer fluids. Being completely concealed by a roof surface, these systems are architecturally integrated into the building design and are hidden from view while remaining highly effective as a power source. These types of solar thermal water heating systems have been rigorously evaluated and have been independently tested by the Florida Solar Energy Center, Cocoa, Florida, and certified by the Solar Rating and Certification Corp in Cocoa, Florida. The Retrofit roofing project includes a new metal roof with integrated solar photovoltaic panels that are cooled by the building integrated solar thermal system and convective airflow along the bottom of the panels, increasing PV electricity output while producing hot water. In addition, upgraded roof insulation and a system to collect and reuse rainfall were part of the Goodfellow Air Force Base installation. A concealed solar thermal system is one of several integrated systems being demonstrated. The first step is the installation of Galvalume steel thermal purlins that are secured to the deck with screws driven through the flanges on the purlins. The channel in the thermal purlins is designed to hold an aluminum-lined PEX tubing that contains the heat exchange medium, which is used for water heating or space heating. Using a special tubing bender, the tubing is fed into the channels in the thermal purlins and tamped into place with a rubber mallet. The bending of the tubing is done with the tubing bender to keep the tubing from being kinked when formed into a given radius. A series of runs with this tubing can be isolated and controlled independently with manifolds. The heat that's transferred through the outer roof is collected by the solar thermal system, located between the old roof and the new roof surfaces. As the heat is absorbed into the water glycol heat exchange fluid in the solar thermal system, It reduces the heat load that would otherwise flow into the building, directly reducing cooling costs by putting the thermal energy to work inside the building for space and water heating. The heated water glycol liquid is used at Goodfellow Air Force Base for preheating domestic hot water and for space heat through an air heat exchanger. In addition, the synergy between the solar thermal system and the photovoltaic system on the new roof is such that the heat that is drawn away from the outer roof surface can help to lower the surface temperature of the PV material, which improves the efficiency of the PV system. An added benefit of the thermal purlins used in the solar thermal system is the air gap that is present around the purlins. This gap allows for natural convective cooling of air that is drawn in at the eave. An unobstructed flow of air can help to dissipate heat from within the roof assembly and lower the heat gain in warm climates. The airspace itself is also an insulating layer to minimize heat loss in cooler climate zones as well. Building integrated solar thermal technologies must prove to be life-cycle cost-effective as the DoD will demand. Instead of being a bulky add-on, the integrated roof assembly results in a hardened building envelope with a high probability of withstanding today's unpredictable weather patterns. There is a growing interest in renewable energy, such as solar, to reduce our dependence on foreign oil and lower the environmental impact of burning fossil fuels. Sunlight is by far the most abundant and renewable energy resource. The use of photovoltaic systems to harness the sun's energy continues to grow. One of the key factors that will contribute to the anticipated global growth of solar power is the progression of functional and technological advancements in the whole spectrum of photovoltaic products. The integration of photovoltaics with metal roofing systems, new and retrofit, is growing. Metal roofing is an excellent platform for thin film and crystalline modular mounted systems. Unlike conventional roof materials, the durability and long service life of metal roofing can outlast the useful life of a typical 25-year warranted PV system. It is common to see the PV system removed and replaced long before the end of a metal roof's service life. This creates significant savings over the life of the PV roof combined asset. An additional fact is that PV of either thin film or crystalline modular types can be mounted to metal roofing without penetrating the roof membrane, which eliminates potential sources of leaks and other maintenance issues. Steel roofing is strong, lightweight, non-combustible, resistant to hail, wind, and weather, and features almost unlimited aesthetics and design flexibility. For decades, our nation's military has used metal roofing for new construction, re-roofing, and retrofit projects. In fact, DoD's Base Structure Report estimates that more than 1.85 million square feet of metal roof retrofits have been installed on military and federal facilities in the U.S. It is further suggested that another 617 million square feet of single-story military buildings will receive metal roof retrofitting. The Goodfellow Air Force Base project involves an existing metal roof retrofitted with a new 24-gauge pre-painted Galvalume steel standing seam roof system. Galvalume is 55% aluminum zinc alloy coated sheet steel that has an excellent corrosion resistance. Galvalume is an internationally recognized trademark of BIEC International Inc. and some of its licensed producers. Inspections of Galvalume roof installations since its introduction to the marketplace in 1972 have suggested the estimated service life of this type of metal roof will exceed 60 years in most climates. Standing seam steel roofing is created with roof panels that are mechanically interlocked together to provide a watertight roof system. The attachment clips are concealed but mechanically attached to the substructure of the building framing, meeting all building code requirements for design loads and resistance to wind uplift. The concealed clips are designed to allow for thermal movement of the metal panels. The installation of the factory roll-formed metal roof system, along with trim, curbs, flashing, and a final layer of insulation, took a crew of 5 men 12 days working in close coordination with other teams installing the building-integrated solar thermal system directly beneath the metal roof surface, along with the sensors embedded in the roof membrane for the Oak Ridge National Laboratory data acquisition system that is monitoring the performance of the building. The pre-painted steel roof used at Goodfellow is Energy Star labeled and listed on the Cool Roof Rating Council's directory. The paint finish is polyvinyl fluoride formulation using special ceramic pigments that are highly reflective in the infrared solar spectrum. Using cool technology in paint finishes allows for darker colors, such as the medium bronze seen here and used at Goodfellow to reflect significant levels of solar energy. The cool roof can help to lower the air conditioning load on the building. Additionally, cool roofs work synergistically with the building-integrated solar photovoltaic system installed on the Air Force Base's roof by helping to cool the PV modules. PV modules operating at cooler temperatures produce more energy and last longer. Another advantage of using cool roofing is that the reduced surface temperature extends the life of the paint systems and also minimizes thermal movement, which prolongs the integrity of the roof system. Cool metal roofing technologies are described in the government's Whole Building Design Guide, a document with a goal of creating successful high-performance buildings by applying an integrated design and team approach during the planning and programming phases. Because DoD and other government agencies follow the WBDG, cool roofing technologies are an important aspect of their buildings. The Department of Defense is interested in solar power installations since it's operating with a federal mandate requiring the DoD to produce or procure 25% of all energy from renewable sources by 2025. That will require installations of many photovoltaic systems across the DoD portfolio of buildings and on federally owned land. More than half of the roofs on U.S. military bases are metal right now. The mandate was partially responsible for the DoD's ESTCP Core grant team selecting a retrofit metal roofing demonstration project that included a building-integrated photovoltaic system. The system, as installed at Goodfellow Air Force Base, features a metal roof retrofit system, metal over an existing metal roof. That includes a laminated thin-film amorphous silicon PV system. To install this type of PV system, the thin film product is first laminated to the top of the metal roof panels using a self-adhered pressure-activated peel and stick adhesive. After cleaning the surface of the metal panel, the thin film is adhered by rolling it into place with a special J roller tool. The laminating is often done in the field, but can also be done in a factory, with panels then being shipped to the site. Once the PV is attached, the panels are ready to be installed directly over the integrated solar thermal water heating system. After the metal panels are aligned and secured from movement, special concealed clips are attached to the seams of the panels and fastened through a bearing plate, through the insulation layers, and into the sub-purlins. The seams are then mechanically interlocked. The final result, after installing the new metal roof, affords an architecturally pleasing appearance with the design line and profile of the metal roof panels. All cabling from the PV modules is run through the ridge cap area to avoid penetrating the metal roof surface. The grid-tied balance of the system includes an inverter, array wiring, disconnects, and other components required by code and good practice. The laminated thin-film PV system was installed over an integrated solar thermal water heating system that is also integrated into the retrofit roofing assembly. The ability to harvest solar energy in the form of heat from the metal roof was important to the success of the retrofit. The ability to utilize the heat buildup on the roof by transferring the energy to glycol-protected heat transfer fluids, which in turn deliver the energy to space and water heating systems, not only doubles the total solar energy harvest of the installation, but it also improves the efficiency of the PV system by cooling the PV panel surface. This synergistic combination of thin-film PV with solar thermal technology as part of the roof is called Building Integrated PV Thermal, or BIPVT. The two technologies, installed during new or retrofit roofing projects, work together to harvest the maximum amount of solar energy to generate power and heat water. It is important to note that crystalline PV systems, as well as thin film systems, can also be incorporated into a metal roof retrofit integrated system. Crystalline PV systems have higher sunlight to energy conversion rates than thin films. But both types of products are compatible with standing seam metal roofing, and both can be attached without penetrating the metal roof surface. The performance data from the demonstration building is being collected and authenticated by Oak Ridge National Laboratory over a one-year period. The data will be used to verify the predicted energy savings from the PV installation on the 11,900 square foot roof. The PV system is projected to generate about 65,000 kilowatt-hours of electricity and save the base approximately $5,200 annually in their electric bill for this building. Equally important to the base, it brings them closer to meeting the federal mandate on the use of renewable energy resources. The Goodfellow Air Force Base photovoltaic system has been in place since June 2012 and is already producing enough electricity to offset 37% of the building's usage based on 2011 consumption levels. More importantly, 2011 was one of the hottest summers and highest usage in recent memory in the San Angelo, Texas region. Goodfellow Air Force Base has an electric grid of their own within the base, so any excess electricity not consumed by the demonstration project building will be fed into their internal grid and used downstream by the next base facility. Bearing in mind that the goal is to provide a minimum of 25% of energy needs away from the grid, this performance exceeds the stated DoD goal. As an added bonus, the AEP Texas North City SMART program for energy efficiency improvement provided a one-time payment of $6,184 to Goodfellow Air Force Base for this improvement, with 96% of this payment credited to the PV system. To learn more about other government and utility incentives for energy efficiency and/or renewable energy improvements, visit the database of state incentives for renewables and efficiency, funded by the DOE, at www.dsireusa.org. The base demonstration project is intended to verify the estimated kilowatt-hours of electricity that can be generated for cooling, heating operation of the building. In addition, the reduction in grid-required electricity will result in a significant reduction in CO2 emissions attributed to the building. The ESTCP project expects to generate data on energy and water reduction that can be used to model the performance of any building being retrofitted on any military base in order to meet their stated energy goals. The success of the Goodfellow Air Force Base ESTCP project relied on having a competent, multifaceted, certified contractor capable of installing multiple unique technologies on the Security Forces building. It was critical the contractor combine the integrated technologies in proper succession for the systems to provide the expected performance. In addition, installation had to be accomplished within the timeline and in a manner compliant with the many rules and regulations of the military base. Competency of construction and keeping within the rules can be challenging, but was done flawlessly with construction management and planning by the contractor. A contractor's team must ensure the integrated technologies, subpurlins, insulation, solar thermal water air heating, photovoltaics, and above-sheathing ventilation are coordinated appropriately into one holistic metal roof system. One cannot overly emphasize the importance of a good contractor to perform what the architect envisions, to fulfill what the manufacturers state their products can do, and to attain what the client foresees as an end result. This is true in any project, including Goodfellow Air Force Base, in which the credibility of the integrated roof system is being analyzed by ORNL and may result in DoD adopting integrated metal roof retrofits throughout its facility portfolio. A holistic, integrated retrofit roof system is appropriate for a variety of building types and occupancies in a variety of climate regions. Integrated building systems, when applied to the DoD infrastructure and/or the commercial building market, can dramatically contribute to reducing energy consumption by providing retrofit roofing, insulation, air barrier, and ventilation improvements along with renewable energy systems in a turnkey package. In addition, a turnkey package ensures that all trades work interdependently under a single supplier that's responsible for delivering the high-performance building system, along with an integrated and often single-source warranty program. Both metal roofing product manufacturers and their certified contractor base have benefited from this, and the industry is rapidly adopting the practice of offering turnkey solutions that deliver higher value to their customer base while driving revenue to their top and bottom line.